Hello from ChemHelp ASAP. In this video we are going to talk about the origins of hybridization. Now, hybridization came about from a scientist, was an idea developed by Linus Pauling. And back in the 1920s, maybe early 1930s, Pauling knew that methane had a tetrahedral geometry. That's the geometry of the bonds coming off of the carbon atom. And it had a bond angle of 109.5. All the carbon-hydrogen bonds were equal. And this is very puzzling. It was puzzling because when we look at the carbon, the orbitals on carbon atom, it has an s orbital and then three p's, px, py, pz. So these are the atomic orbitals on carbon. And it's kind of weird that these four different orbitals on carbon could somehow make four equivalent CH bonds. So Pauling developed an explanation for this. Pauling said, let's take the four atomic orbitals and somehow we will combine them together, and this is the hybridization. And we will generate four new atomic orbitals. And Pauling called them sp3 hybrids. So you can see where the name comes from. We put in an s and 3p orbitals and we make sp3 hybrids. Now it's important to note we have four orbitals in, four orbitals go into the hybridization, and we get four orbitals out. That's important because the valence or the octet rule for methane still applies. And for the octet rule, we need 8 electrons, and to hold electrons, we need 4 orbitals. So we have to preserve the number of orbitals. With these four equivalent atomic orbitals, Pauling was able to explain why all four CH bonds in methane are equivalent. Furthermore, Pauling didn't stop at sp3 hybridization. Pauling developed the ideas of sp3, sp2, and sp hybridization, all three of these different hybrid models, to explain furthermore other molecules and their geometries and bond angles in addition to simply methane. As it turns out, the hybridization model works very well for second row elements. And when I say the second row elements, it works best and is most commonly used for carbon, nitrogen, oxygen. That doesn't mean you can't use it on boron or fluorine or even the halogens from the other rows of the periodic table. And also sometimes people will apply it to sulfur and phosphorus. But really, at its heart, it's best for these elements. With the hybridization model that Pauling developed, we can explain things like, just like Pauling, the geometry of our atom, we can explain bond angles, and we can even in some cases use it to explain reactivity of our atoms. But that's a little bit of a stretch for hybridization. At its heart, it's best for geometry and bond angles.